Exercise 23. So the additive group of integers is given. We have been asked if every subgroup of this group is cyclic and why. What is the reason for our answer? And also we have been asked to describe all the subgroups of this group. So that is the first part, and then in the second part, any element A in some group is given which has infinite order. We have to describe all the subgroups of the cyclic group generated by A. So because A has infinite order, so the cyclic group will itself be infinite. So let's see the solution. Since the additive group of integers is itself a cyclic group which is generated by the integer 1. It is also generated by -1, but you need to show only one generator to show that it's a cyclic group. So theorem 4.3, which is the fundamental theorem of cyclic groups, implies every subgroup of Z is cyclic. The subgroups of this group are the cyclic subgroups generated by non-negative integers. Which you know is the set of all integers of this form, that is all multiples of n, where this m varies over the set of integers, where n is a non-negative integer. You may ask what happens when you take a negative n. But because this is a cyclic subgroup of the original group, so if you take a negative n, then it's quite easy to see that it will be equal to this one. Okay, I mean, if you take a negative n here, for example, if you take -1, then one can show that that is just equal to this minus of -1, which is nothing but the entire group. Like that, for every integer n, the cyclic subgroup generated by n and the one generated by -n in this group are the same. So there is no need to consider negative values of n here. We won't get anything new. We will get only the the ones we already have here. Okay, so these are all the subgroups of the additive group of integers. So just like that, the subgroups of this cyclic group, this second part also will follow from theorem 4.3, which is the fundamental theorem of cyclic groups, are this where I is a non-negative integer. Okay, so this is the solution. Then 24. For any element A in any group G, prove that the cyclic subgroup generated by A, subgroup of G of course, is a subgroup of C of A. C of A is the centralizer of A. So we have to show, let us recall that the centralizer of A consists of those elements in G that commute with A, and we already know that they form a subgroup of G. We have to prove that this is a subgroup of this. That means any power of A, any integral power of A, because a typical element in this cyclic subgroup is an integral power of A. It will belong to this. That means we have to prove that any integral power of A commutes with A. So let A to the power I belong to this cyclic subgroup where I is some integer. Then by the rules of exponents, which is true in any group, we have this. A to the power IA is equal to A to the power I plus 1, and this is true for any integer I need not be positive or non-negative for this to be true. I can be any integer. Now because addition of ordinary integers is commutative, so we can write it like this, and this again by the rule of exponent A to the power I. Actually, ideally I should have written one more step here, where in place of A I should write A to the power 1, which by the definition of integral powers is nothing but A, but that I choose to not write. Okay, it's understood, which implies so that means what? A to the power I commutes with A. So A to the power I belongs to the centralizer of A. Hence, the cyclic subgroup generated by A is contained in the centralizer of A. That is, this is a subgroup of CA. Note that simply this inclusion does not mean this is a subgroup of CA. It's because both of them are groups and the binary operation in both of them are consistent, in the sense that if you restrict the binary operation of this to this subset, then that becomes the binary operation on this. That is why we are able to say that this is a subgroup of Ca. So this is the solution. Next, (25). If d is a positive integer, d is not equal to 2 and d divides n, where n itself is also some positive integer, show that the number of elements of order d in the dihedral group Dn is phi of d, where phi is Euler's phi function, which calculates the number of positive integers less than d and relatively prime to d. Okay, so that is the first step. And also, how many elements of order 2 does Dn have? Okay. Keep in mind that Dn itself is not a cyclic group. This we already know. So we cannot apply any result about cyclic groups on the entire Dn, because it's known to be not a cyclic group. So we have to be careful before we apply something. So the thing here is that d is some positive divisor of n that is different from 2. We have to show that the number of elements in Dn which are of order d is phi of d. Okay. So in particular, we are looking for elements whose orders are of course d, and that's why none of them is of order 2. So we start the solution like this. Since, and let us also recall, since we are dealing with the dihedral group Dn, let us also recall that Dn has two types of elements, reflections and rotations. Since every reflection in Dn has order 2. This is already known, except of course the identity, which I don't think you can think of it as a reflection. No, it is a rotation through an angle 0 degree. Anyway, so every reflection in Dn has order 2. So the elements in Dn of order d are all rotations that is they are all, okay, let me just refill. That is, they are all elements of the cyclic subgroup A where A is the rotation through an angle 360 degree divided by n. This we already know about dn, namely the rotations form a cyclic subgroup and this is the smallest possible rotation. This is the smallest possible rotation, that is a symmetry of a regular n-sided polygon. Okay. Now note that the element a to the power n by d belonging to dn has order d. Recall that this subgroup consisting of all the rotations in dn has order n. That is because this element that is generating this cyclic subgroup is of order n. And using that fact, one can prove that the order of this element is d. Okay, it's not very difficult. You just need to apply the rules of exponent. The rules of exponent will give us this will be equal to a to the power n. Now since a has order n, so this is the identity. That is one thing. Now if you suppose that a smaller power means a power where the exponent is smaller than d is also equal to identity. Say this is what you have supposed for some positive integer I less than d. Then what do we get? Ni divided by d is equal to r naught. Okay. Now what is ni divided by d? Ni divided by d is less than n. This follows directly from this inequality. So that means this is a positive, it's an integer. It's an integer because n is divisible by d. So n by d is an integer. So if you multiply that by I, that is also an integer. So this is a positive integer smaller than n, for which this equation is true, and that contradicts the minimality of n, because n is the order of a, means n is the smallest positive integer such that a to the power n will be equal to identity. So that is a contradiction, and that contradiction stems from this supposition that such an I exists. So such an I cannot exist. So d is the smallest positive integer for which this equation is true, and that is why d is the order of a to the power nt. That's what we have written here. So this is the justification. Okay. So now we have found one element in Dn of order d. So that means what? The cyclic subgroup generated by this element in Dn will be of order d. I think that's how we have proceeded here. Let me just see. Yes. So the cyclic subgroup has order d. Now we invoke theorem 4.3, the fundamental theorem of cyclic groups. By theorem 4.3, this is the this uniqueness is what will help us in this solution. This is the unique subgroup of this of order d. Note that we have to apply the theorem 4.3 only inside a cyclic group, and our cyclic group is this. We cannot apply the theorem on the entire Dn because that is not cyclic. So what is this theorem saying in this case, the way we have applied it? It says that if you have a cyclic group of order n, and say k is a divisor, k is the positive integer that divides n, then the cyclic group has exactly one subgroup whose order is k, and that subgroup, if the original cyclic group is, say, generated by some, to distinguish it from that A, let me denote it by B. So this is our cyclic group which has order n, and k is a positive integer that divides n. Then theorem 4.3 says that this group has exactly one subgroup of order k, and that subgroup is this. This subgroup is unique. Okay. Now, how will this uniqueness help us? That is the point. If there is, let us just write like this. Now, for any element say B belonging to A of order D. We have already noticed, we have observed the fact that the elements of order D are all rotations. So the fact that we are considering such an element B from this cyclic subgroup of all rotations, doing that we don't lose generality. These are the only elements in Dn that are of order D, because we cannot take reflections. Reflections are not of order D, they are of order 2, and D is not equal to 2. Okay, so for any element B of order D, the cyclic subgroup generated by B is of order D, because the element that is generating the cyclic subgroup has order D, so the subgroup also must have order D. Now, because of uniqueness, this will be equal to this. The above uniqueness then implies and hence the element B belongs to the cyclic subgroup generated by itself, so B will also belong to this. Oh no, wait, this is not what I wanted to write. The uniqueness does not imply this, the uniqueness implies this. Yes, because this is the unique subgroup, and hence B belongs to this. So now our search has been narrowed down further. First we were searching for elements of order D in the original dihedral group. We then figured that those elements cannot be reflections, they are rotations. So we have narrowed our search down to this cyclic subgroup consisting of all the rotations. Now our search has been further narrowed down to this cyclic subgroup of this subgroup. Okay. That is because now we see that any element B of order D must belong to this subgroup. Now we can use another result to count the number of such elements. Now, by the third corollary, corollary 3 to theorem 4.2, I think. Yes. So any such B will now be an integral power of a to the power n by d. For any integer, positive integer, say j, that is less than d, the order of what will it be, a to the power n by d whole to the power, yes, this is equal to D, which is let us just also mention this fact that it is the order of a to the power n by d. If and only if J and D are relatively prime, hence so the number of such J's is precisely the number phi of D, and that many elements we will have in this subgroup which have order D. Each one of them has order D. Hence the number of elements here of order D is phi of D, since all the elements in Dn of order D must lie inside this cyclic subgroup the number of elements in Dn of order D is also that thing, phi of D. So that is the first half of the solution. In the second half, we have been asked to find the number of elements of order 2. This we already know. If n is odd, then there are n elements in Dn of order 2, which are all the reflections. On the other hand, if n is even, then there are n plus 1 elements of order 2. One extra element comes, which is a rotation then there are n plus 1 elements in Dn of order 2, which are all the reflections along with the rotation. A is like before, A is this A, a to the power n by 2, which makes sense because now n is even. So this completes the solution. Then 26. Find all the generators of the additive group of integers. Let A be a group element that has infinite order. Find all the generators of the cyclic group generated by A. Okay, so first we have to deal with the additive group of integers. We already know that 1 and -1 are generators, but are there any other generator? So that we have to figure out. Let n belonging to Z be a generator of Z, that is the group is generated by the integer n. We have considered n to be some generator of Z, so it may be a negative integer also. Since 1 belongs to Z, so according to the definition of this cyclic group, and because the operation here is ordinary addition, so this cyclic group is the set consisting of all integer multiples of n. Now because 1 belongs to this, so 1 will also belong to this cyclic group, so 1 will be an integer multiple of n. So 1 is equal to nm for some integer m. But now n and m are integers and 1 of course is an integer. So there are only two possibilities, either both n and m are equal to 1 or both of them are -1. This implies either n is equal to n, which is equal to 1, or both of them are -1. So the point here is that n is either 1 or -1. Thus the only generators of this are 1 and -1. Similarly, one can show that the only generators of this is the second case, this is that other part. A is a group element of infinite order, so the only generators of this cyclic group are a to the power 1, which is A, and A inverse. You have to argue similarly, but in this case in the general cyclic group, this I leave the details to you. So the solution ends here. Then exercise 27, prove that C star, the group of non-zero complex numbers, under multiplication. That's what this denotes, has a cyclic subgroup of order n for every positive integer n. So here in the solution we just have to actually show the cyclic subgroup, because we can, and that's how the solution will be presented. Consider the complex number omega equal to cos 2 pi by n plus I sin 2 pi divided by n. Since the absolute value of omega is equal to 1, omega is not equal to 0. It's a complex number of absolute value 1. So it is a non-zero complex number naturally, because only the 0 in the system of complex numbers has absolute value 0. That is, omega belongs to C star. Okay, so now next our aim is to show that as an element in this group, omega has order n. Note that omega to the power n, this is a place where we have to use that de Moivre's theorem. So this becomes n times 2 pi by n plus I sine n times 2 pi by n, and that is cos 2 pi plus I sine 2 pi. Cos 2 pi is 1, we know from trigonometry, and sine 2 pi is 0, so this is 1. And note that 1 is the identity element in this group because it's a group under multiplication. Suppose omega to the power I is equal to 1 for some integer, positive integer I, strictly less than n, then I don't actually remember if we have already shown that the order of this complex number is equal to n, not using these terminologies order, but we may have already shown that the smallest positive integer I for which omega to the power I is equal to 1 is n. That we may have shown. I cannot remember. If that is already shown, that there is no need to go through these things. Anyway, so then what do we get? Then cos 2 pi, we will confuse this I with the imaginary unit. So let us take j. Two pi j divided by n plus I sine 2 pi j divided by n sine 2 pi by n whole to the power j. This is equal to 1. Okay, which implies cos 2 pi j divided by n is 1 and sine 2 pi j divided by n is 0. Now from elementary properties of trigonometric functions, if you go back to that part of trigonometry which tells you how to solve this equation, you will get that you will get the fact that this is not possible, that for such a j that is less than n, this cannot give you 0. Sine of this real number cannot be 0. Just like that, cos of this real number cannot be equal to 1. But shall I write it like this or should I supply more detail? That's what I am thinking. Maybe like something that will show without leaving out anything that yes, we get a contradiction. Let me just think of that. it's easier to use this equation from sine 2 pi j divided by n equal to 0, we have when sine of some real number is 0, that real number, you have to understand that if we are not using any unit for the angle, then the angle is in radian. Okay, that is the convention. But if we are using, if we mean degree, we have to explicitly write degree. So that means here the angles are in radian. So if sine of some angle is 0, then the angle should be an integral multiple of pi radian. So from that we have 2 pi j divided by n equal to k pi for some integer k. Now what do we get from this? This implies pi of course will get cancelled. This implies, so what now happens to j? J is equal to kn divided by 2. Oh, so we are getting n divided by 2. So that won't immediately give me a contradiction, will it? The only information I have of j is this, that j has to be less than n. Okay. J has to be equal to kn divided by 2. I do get a contradiction if n is odd, but who is saying that k is not even? If k is odd and n is odd, then there is a problem. Otherwise, we don't see any problem. No? Is there an easier way to show that for such a j, this equation is not possible? I am missing something. Cos 2 pi j divided by n plus I sin 2 pi j by n is equal to 1. So this is equal to 1. Oh, I haven't used this equation. What does this tell us? Cos 0. Okay. Two pi j divided by n 2k pi plus minus 0, that means 2k pi. Okay, where k is some integer. Okay, so here 2 and 2 they cancel, they get cancelled. K and pi and pi they also get cancelled. So j should be equal to k. Yes. The easier one doesn't give me anything. I have to use the first one. From cos 2 pi j divided by n equal to 1, we get 2 pi j divided by n equal to 2k pi for some integer k. cos theta is 1 if and only if theta is an even integral multiple of pi, or if and only if theta is an integral multiple of 2 pi. This implies j equal to kn. Okay. Now we can use that inequality, this one, and try to get a contradiction. I think we will get some sort of wrong result or wrong statement that will give us a contradiction. So j, if I put j equal to k, and then what happens to k? Yes. Hence 1 is less than or equal to kn, which is less than n. Is there a problem with this? The inequality, because we now want a problem. The first inequality implies what? Implies k is positive. Okay. Simply because k is greater than or equal to 1 over n. N is already positive, that we know. Or let me just show that also. K is greater than or equal to 1 by n, and 1 by n is positive. However, thus inequality kn less than n implies that k is less than 1. So yes, this is the contradiction. 0 is less than k less than 1. This is a contradiction because there is no integer that lies strictly between 0 and 1. This is a contradiction. And hence our supposition is wrong. That is, omega to the power j is not equal to 1 for all integers positive integers j less than n, which means what? It just simply means, combined with this thing that this power is 1, it just means that the order of omega in the multiplicative group of non-zero complex numbers is equal to n. So in the group C star, this is equal to n. We are having a notational difficulty here. This symbol simultaneously means, because this is a complex number, the absolute value, but also it means the order of the element omega. That's why we are writing. So in the group C star, when you see this thing, this phrase, you should understand that this means order, okay, not an ordinary absolute value. As an element of this group, the order is n. Hence, this is a cyclic subgroup of C star of order n. And n was chosen to be any positive integer. So this is a cyclic subgroup. Geometrically, the elements of this subgroup will lie at the vertices of a regular n-sided polygon, which is inscribed inside the unit circle centered at the complex number z equal to 0. Why that I'm not going to say, and we don't need that also. Next exercise 20. You can think of something, if you know about what complex number multiplication means or what it does to points in the complex plane. When you multiply two complex numbers, their arguments are added. From that you can figure out that geometric thing that I have said right now, keeping in mind that when we multiply omega with itself n times, we circle back to 1, the complex number 1. Anyway, the next one, let A be a group element that has infinite order. Prove that the cyclic subgroup generated by a to the power I is equal to 1, the one generated by a to the power j, if and only if I is plus or minus j. And in this context, it's obvious that I and j are integers. Okay, so we have to prove an if and only if statement. That means there are two things to prove. If this is true, then this is true. Let us show that one because it seems easy. If I is j, then obviously the cyclic subgroups are the same because it's just one element. If I is minus j, then minus j, which is, if we use the rules of exponent, this is the inverse of a to the power j, and we know that in any group an element and its inverse generate the same cyclic subgroup. So one half of the statement is, it has been proved. Next, assume that this is equal to this. Since a to the power I belongs to the cyclic subgroup generated by it, and just like that, this belongs to the one generated by it, we have, because of our assumption, this belonging to this and the other way around. Hence, a to the power I belonging to this means what? A to the power I will be an integral, an integral, I was going to say integral multiple, an integral power of a to the power j. So that means this is equal to this, which is equal to a to the power alpha j and beta. We don't know what alpha and beta are, but there will be some integers, alpha and beta. Okay. Now, a to the power I minus alpha j is equal to, it's not 0, it's the identity element in the group. Wherever this a is an element, it's the identity of that group. This is also coming from the rules of exponent, and just like that, a to the power j minus beta I is equal to identity. Okay, now what happens if these exponents are non-zero integers? Suppose this is a non-zero integer. Being a non-zero integer, it can either be positive or negative. Let us write one more step. These imply absolute value of this is equal to identity, and j minus beta I, this is also equal to identity. What is the reason? Think of some concrete integer in place of I minus alpha j, say 3. You can have either this, or you can have some negative integer also, say a to the power minus 4 is equal to e. These are two different cases, okay. In the first case, the exponent is positive, so in its place you can also write this, nothing changes, because this is again 3. Now what about this one? If the exponent is negative, then this is also equal to identity, and by the rules of exponent this becomes this. And what is 4 now? 4 can be written as the absolute value of minus 4. So you see that whatever integer you have here, either positive or negative, you can replace that by its absolute value in the equation and get equations like this. So now what happens? This we have understood how these absolute value versions are coming from the original ordinary ones. Now note that in both these equations, the exponents are non-negative integers because of the presence of absolute values. Now it is given that A has infinite order. So for no positive integer m shall we have this. Because if that is the case, then A will have finite order and the order of A will be at most m. So that means the exponents cannot be positive integers, but they are already non-negative, so they must be equal to 0. Since I minus alpha j and absolute value of j minus beta I are non-negative integers and A has infinite order, we must have both of these equal to 0. Thus, I should be equal to alpha j and j should be equal to beta I. Okay. We now have what? I equal to alpha beta I. We have used j equal to beta I here. Okay. Now what happens if I is 0? Beta can also be 0, no? No, I mean I can be 0 and alpha can be 0 without making j 0. Oh, but if I is 0, then j also has to be 0. Okay, yes. If I is equal to 0, then j equal to beta I is also equal to 0 and we have, then automatically we have I equal to plus or minus j, obviously. So assume I is not equal to 0. Then on under this assumption, we can cancel I from both sides of this equation. Then I equal to alpha beta I implies 1 is equal to alpha beta. Now alpha and beta are integers, so alpha beta will be 1 in two cases. We have already seen one such situation. Thus either both of them are 1 or both of them are minus 1. This finally that means either alpha is 1 or yes, either alpha is 1 or alpha is minus 1. So that means either I is j or I is minus j. So that is the solution in its entirety. Then exercise 29. List all the elements of order 8 in this is okay. List all the elements of order 8 in this somewhat large group. Modular group, but a very big group. How do you know your list is complete? Let A be a group element, then the general version. Let A be a group element. A is coming from some group. Such that its order is this big number. List all the elements of order 8 in the cyclic subgroup generated by A. Subgroup in the original group from where A is coming. And in this case also, how do you know your list is complete? There is an easy answer. You can say I don't know. Okay, that option is also there. So the group here we know all modular groups are also cyclic. So this one is also cyclic, and its generator is 1. Okay, that thing is there. Don't think that its generator is this. Since this is equal to 1, where you should understand that the operation is addition modulo this number. So the element 1 has order equal to this. Okay, it's not our ordinary, although in this book the elements of this are being treated as ordinary integers. Strictly speaking, they are not, they are congruence classes. But still, since we are in a group, it does not really matter what we treat the elements as, because there is no difference between two isomorphic groups. So if we think of this as the congruence class containing 1 modulo this, or as an ordinary number, as the ordinary number 1, it does not matter as long as the two interpretations of this group give us isomorphic groups. Okay, so since this is a cyclic group, that is the point here, since this is a cyclic group, there are phi of 8 which is equal to 4 elements of order 8, and for this we have already seen why this is the thing. See the solution to exercise 25, and they are obtained from those values of j, if you remember, where j is an integer less than 8 and relatively prime to 8, that is these elements. These elements will have order 8, where in place of a we have 1. So actually we should have written this: j is less than 8 and relatively prime to 8. Don't think that 1 to the power j is 1. It's not your ordinary power. In this additive group, 1 to the power j really means 1 plus 1 plus 1 j times. Okay, so this is j. And now, am I saying it correctly? Let me just... No, I am not saying it correctly. Because in the solution to exercise 25, this part we have written correctly, that is okay, but this is where I made a mistake. Actually, the subgroup in which we found the elements of order d is not this, no, it is this. So that means instead of 1, here we should have, let me clean this part. We have to understand it properly, what we are doing and what we are going to write as something that we know. There should not be any doubt about that. A is the original generator of the group, so which in our case is 1, okay, and the subgroup in which we will find the elements of order d is this cyclic subgroup. In our case, n is this number and d is 8. So we are looking for elements of order 8 in this cyclic subgroup, which is now what is this element? This element does not mean 1 to the power this number in the ordinary sense, but a sum of this many ones. So that is this cyclic subgroup actually. This is where elements of order 8 will appear. But what type of elements? Namely, those elements for which we have this. And here again, this power does not mean ordinary power, but actually it means this times j, because we are in additive group. And you know what these integers are: 1, 3, 5 and 7. So the corresponding elements of order 8 in this big modular group are this, then the 1 where in place of 1 you have 3, and then the one where the number starts with 5 and the one starting with 7. And they are, so I am just writing it directly here, but you should understand that from the solution to exercise 25, this is how the elements are coming, and the elements are this. Okay. And what is the second part? The second part is similar to the first one. The only difference is that here we have a general group element and its order is given. So there also you can use the solution to exercise 25 and get the things similarly. List all the elements of order 8. The elements in these are so that's where the solution ends. Keeping it short, not saying all these things, not making this a part of the solution. And finally, today's last exercise, definitely not the last exercise of this set of exercises. There are many. I think now we will be doing 30th. No, there are 86 exercises. So in each video we will try to attempt at least 10. Attempt means solve. Hopefully all of them we solve. At least 10. In this video, of course, it's smaller than 10, less than 10, but we have got to 30 and then we will get to 40 and then 50, 60 like that. Suppose A and B belong to a group A has odd order and A inverse is equal to B inverse. Show that B square is equal to identity. This is not really so much about A having odd order, but it's really about A having a finite order. That's what matters. Let order of a be equal to n, which is a positive integer and it's odd according to the hypothesis. Now a b a inverse equal to b inverse implies what? If we 3 multiply both sides, no, not like that. Shall I get anything new by doing that? Or taking inverse on both sides. This implies b is equal to b inverse whole inverse, that is equal to the inverse of ab a inverse b inverse and no, I was wrong. I think okay, now I think I see what is happening. Okay, we will see. So a inverse, n being odd will matter. A b inverse a inverse, we will see. Okay, I think for a moment I saw something in these calculations that made me believe that we should have an odd n, otherwise there will be problem. Let us see what happens. So let's for now let's keep n as just n. Now we have an expression, we have an equation which expresses b in terms of b inverse. That can again be used in this equation itself. Hence, b is equal to a b inverse a inverse. Now in place of b here we can again use this expression a b inverse a inverse inverse a inverse. So just like that, this calculation, if we proceed, what shall we get? A inverse will be A. Oh, that's why we need odd. Yes, we will need odd n. I don't know why I thought only finiteness of n is what we need. A square b a to the power minus 2. Okay. Again, in this b, if we use a b inverse a inverse, then we get a to the power 3 b inverse a to the power minus 3. And let us do one more step. This is equal to 2 more steps actually, 2 more substitutions. A b inverse a inverse inverse a to the power minus 3. So here again b inverse will be b, and we will be left with a to the power 4b a to the power minus 4. and one more substitution. Now we look at these steps. This one, this and this. Whenever the exponent we have over a that is even, we have +1 here. Whenever the exponent is odd, for example, if it's 1, 3 or 5, we have -1, -1, -1. If the exponent is 2 or 4, we have 1. And in the next stage, you can clearly see from the pattern that this calculation is following. In the next stage, we will have a to the power 6, b a to the power -6. So if we proceed like this, since the exponent of a is increasing, at some point it will get to n. And because n is odd, we will have b inverse here. Now, since the order of a is n, both these powers will be equal to identity, and that is why we will be left with b inverse. So b is equal to b inverse. Thus b square is equal to identity. So this completes the solution. So we will see other more exercises and their solutions in the next part. So until then, it's me, Lucifer, from a mathematical room. Have a nice night.